Okay. So if you recall last time, where we were trying to understand the following phenomena, where if you wanted to understand is that we wanted to do pre-processing, and for the vertex cover problem, right? We wanted to say that, look, in the beginning, we found a set W, right? So our first branching algorithm was based on set W, such that W, there exists an optimal solution S of size at most K, such that S intersection W is not equal to 5. So we designed our first algorithm based on that, okay? And then we realized that, in fact, we can take W equal to U comma V, UV is an edge, right? And get actually 2 power K algorithm. Okay. And then I had given you exercise at this point of time, is that our exercise was, could we design a C power n algorithm for vertex covered where C is strictly less than 2, right? By what was that? Using this 2 power K n to the power big of 1 algorithm and n choose K enumeration algorithm. Enumeration algorithm. Okay. How many of you have tried? If you have tried, please put +1. I'm not asking numbers. Okay. So if you have tried, can you write your numbers? What number did you get? Okay. What C did you get? Okay. Others? Okay. So what is 2 point? Okay. Power 0.7. Yeah. I think it is same. Yeah. So yeah. So basically everybody has got this. Okay. So yeah, this is what you will be able to get. 1.709 to the power n, n to the power big of 1. Okay. Okay. Now here's a curiosity question. Okay. Explore. Okay. Suppose vertex cover had 7 power K algorithm. Suppose vertex cover or vertex cover star, some new problem, had 7 power K n to the power big of 1 algorithm. Does it imply better than C power, better than 2 power n algorithm for the corresponding problem? Okay. So rather than having this 2 power k algorithm, imagine that you had 7 power k algorithm or 10 power k algorithm. Does it imply a better algorithm? Okay. So just think about it. Like, this is not something which I expect you to come up with an answer or something, but like worth to think about it. Okay. Now we moved on. We took this idea and direction. I said, okay, so this overall idea of finding a set W such that S intersection W is not equal to empty is interesting, right? And then we said, is it possible that in a graph G, I can come up with a W, right? And I can come up with S, right? Like basically S inside W inside VG, and running time to get W is still poly time. Okay. And what is the property? That we wanted cardinality of W to be as small as possible. Okay. And then we got into this, then we started with vertex cover, right? And try to design such a W for vertex cover. And what did we say? We said, okay, let's apply following reduction rule. Rule 1. Remove degree 0 vertices, right? That was our first rule. Then we also came up with rule 2, which we said is that, what is the rule 2 we said, if you recall correctly, is that if there is a vertex V of degree 1, then G minus neighborhood of open neighborhood of V, right? You delete that, and K minus, right? So if we had a neighbor, so you just looked at its neighbor, deleted it, and you applied this. This was the second rule we applied. And rule 3 was, what was the rule 3? High degree vertex rule, right? High degree rule. So what was the high degree rule? If there is a vertex V of degree greater than equal to K plus 1, then G minus V, K minus 1. Is that all fine? Right? And in fact, what we were able to prove last day, that in fact, what I'd be able to get, that from GK, we can get an instance G prime, K prime, such that vertex set of G prime was 2 times K square. Am I right? And the number of edges in this graph was at most K square. Right? So our W in this case was precisely vertex set of G prime. Okay. So in our world, this kind of transformation has a name. Okay. This transformation has a name. Okay. And this is called preprocessing, kernelization, whatever you want to call it. Okay, it doesn't matter. Okay, but this is an overall structure. Okay, so what happened? So I'm not going to give you a very formal definition. So you're getting. I'm only going to talk with respect to vertex cover. So what is the objective in the vertex cover? Given G comma K, I need to run in polynomial time. Okay, and output an instance G prime K prime with some properties. What is the property? G comma K is a yes instance if and only if G prime K prime is a yes instance. Of course, a vertex cover, because that is what we have been talking about every time. Still, everything is about vertex cover. We are not talking about anything else. You will make algorithm for everything. Okay, that's one thing. That's one property, that the algorithm runs in polytime. So this is actually, there are three properties. First, runs in polytime. Second, it preserves the answer. And the third, there's just some size constraint. What we want is basically Vg prime plus number of edges, right? Plus K prime should be polynomial. Okay, so everything, total size of the output should be bounded by a polynomial function of K. Okay, some remarks to make, right? Remarks. What are some remarks? Look, so whenever you mean size of the reduced instance, I will mean everything. Vg prime plus E of G prime plus K prime. Okay, everything. This is the size of the reduced instance, means sum of all these things. Okay, and ideally, okay, what is the K prime, if you notice, is going to be always less than equal to K. Okay, though I do not say that K prime has to be K. Okay, we will never demand K prime is less than equal to K. But for all the things which we will be doing, K prime will be less than equal to K. Okay, we will come back to this situation and tell you when this kind of situation is useful for us. Okay, but not now. Okay, in everything, what is our goal? We were looking to find a vertex cover of some size. We have been able to identify some vertices in our solution. We delete it. So in the reduced instance, we are trying to find a vertex cover of smaller size, okay, or equal size. Okay, so that is my motivation. Okay, but now people say, look, algorithmically, notice, algorithmically, okay, okay, algorithmically, if you notice, if I wanted to design an algorithm for vertex cover, right? Now, what are we able to do? Here it is, okay, fine. Vertex set of G prime is bounded by 2 times K square, right? 2 times K square, okay? So algorithm wise, it is 2K square, choose K, right? What is this runtime time? Anybody?
K to the K.
K to the power K, yes. So this will going to be 2 to the power big of K log K, right? But now notice, I did not, if my whole idea was not to reduce the whole size, but even if G prime, vertex set of G prime was say N, but cardinality of W was say 4K, right? Then what will the running time of this algorithm will be? 4K, choose K, right? So what is 4K choose K is less than equal to 2 to the power 4K for sure. So which is 16 to the power K, right? So for algorithm, it is not necessary that we reduce the whole instance. It is just good enough for our purpose that we find a set W which is as small as possible, right? So now, given a problem, we could have two different questions. Trying to find a place which will give me a faster algorithm. There could be a different, altogether different strategy to reduce the everything, like reduce the whole size. Now, I mean, people do all kind of these things to design algorithm, okay? But let us look at this paradigm. Okay. For a first time, I'm going to change a problem. Okay. So for the max matching, what is the max matching problem? So max matching problem, input is G comma K. Okay. Question. The G has a max matching of size, or does G has a matching of size at least K? Size at least K. This is my question. Now my question is, can we make this box for max matching? So what we want to say, in polynomial time, I want to produce G prime K prime with the following property. G has a matching of size at least K if and only if G prime has a matching of size at least K prime. Anybody?
We can find
What?
If there is some isolated edges,
Okay.
then we can remove that and then reduce K by that number of size.
Correct. Yeah, that's a rule. Okay. I forgot to add, right? Like the third, we also had some property, right? Right. Sorry. We also want this property, no? Otherwise, it's trivial, right? You will just give me the same thing. Yeah. Otherwise, you will cheat me. So you are not allowed to cheat me, no? So I also want this property. Otherwise, you can just return me G comma K and say, hey, all is well, all is well. No, I don't want you to do that. This is just conceptual thing which I want you to understand. It's trivial. Okay, so claim. Another hint. Do you need hint or do you want one more minute to think?
So if we have a event cycle in the graph, the say the cycle length is say K, so say any D, then we can alternate pick the alternating edges in the event cycle and reduce the size by D by 2.
Huh. So what you want to say that you find a cycle of length this, pick up this alternate, delete it, and do the thing, right?
Yes.
Who will prove the correctness? Then you have to prove there exists a matching of size at least K that contains the D by 2 edges which you have selected. Otherwise, I can't apply this rule. Okay, so let me give you a hint. V of G prime has two vertices. In fact, one vertex is good enough. Look back. Hello? Who's saying?
I'm Satya.
Yes, so much noise. Say.
I'll solve the problems.
Okay. Okay, I understand what you're saying. Fine. Okay. I'll mute you. But I know what you said. Okay. Okay, so what he's saying is following. And that is exactly what the point is. Do I have a power of polynomial time, right? And finding a maximum matching is polytime algorithm, right? Yeah. So what is my algorithm? My polytime transformation. Polytime transformation. Find a maximum matching M of G. Right? Okay. Second, if cardinality of M is at least K, then what is this? This is an yes instance, right? So let's return a yes instance. So what do I return a yes instance? I make a vertex and I ask 0. This is my graph. This is my return. What I'm asking, does this graph have a matching of size at least 0? Answer is yes. I have not changed the answer. Okay. So you will return this. If cardinality of M is less than K, then what you should return? No. So let's make a no instance, no? Return. This is my graph, this is 1. Does this graph have a maximum matching of size at least 1? Or matching of size at least 1? No. So I have preserved the answer, right, in a correctly. And I have returned you an instance of what size? Constant size. So what did you know? For any polytime algorithm, I can do this transformation, which will transform the problem, an equivalent problem of constant size. Okay, I just wanted to tell you that the whole machinery that we just built, it encompasses P. It encompasses every polynomial time solvable algorithms. Right? I mean, so please pause and think about it for a couple of minutes. I mean, it is nothing, but it's a conceptual like jump. So I want you to take that conceptual jump with me. Right? So let's go back. What is the property of this? I could have written any problem here, which is polytime solvable, and came up with some decision question and asked some polynomial. So I'd have run that polytime algorithm, right? Based on the answer of that polytime, I would have constructed yes or no instance of a constant size and returned. And now, because we have solved, because of the correctness of this polytime algorithm, the correctness of equivalent instance is also correct. Right? So notice, if a problem is polytime solvable, we can come up with an equivalent instance of constant size. And that's perfect, right? Because if I return you this constant size, a graph containing a single vertex and 0, you can check, right, in constant time, whether this and return yes. Yes. So our initial graph had a matching of size at least K. And that's a correct answer. If I give you a single vertex and 1, you can just look at this single vertex and say, hey, no, this single vertex graph has no matching of size 1, which implies that original graph D did not have matching of size at least K. So look, if for polytime, it's perfectly okay to have such objects, right? Such constant size returned, constant size, what do you call it? Graphs or instances returned at the end. But if the problem is NP hard, should we think of such return? So, question. For NP hard problem, right? Say, or for, I don't want to talk about NP hard problem, okay? for vertex cover problem, and the vertex cover problem is my canonical problem. For vertex cover problem, could we come up with an equivalent instance with size, say, order log n. I'm happy that even if you reduce the total instance to log n, like number of vertices, with y size, with number of vertices being order log n. Is it possible? If you did, what will happen?
No, it is not possible.
Right?
Good force, yes.
Right? Because then in 2 to the power big O of log n time, I can solve the reduced instance, right? And after solving that reduced instance in 2 to the power log n or 2 to the power k, we know all algorithm. In fact, k up to log n, we know an algorithm, right? We can run that algorithm and in poly time decide this cannot happen, right? Then decide. So what do we know? So what did we learn? So suppose we have a vertex cover. This is a vertex cover, okay? And G comma K, poly time, okay? G prime, K prime say less than equal to K, and say vertex set of G prime is less than equal to say order log vertex set of G, right? Even such transformation not possible. So what theorem we can show? Unless P equal to NP, right? No polytime transformation exists. Such that reduced instance has order log n number of vertices, right? So P versus NP itself gives us some lower bounds for these kind of objects. Okay? Is everybody okay with this statement? If yes, please put +1. Okay. So for vertex cover, let us see. So let's talk only in terms of number of vertices, because that itself seems to give us something very interesting, right? So here is a world. Let's consider the world of vertex cover and polytime or polytime transformation. So from now onwards, I'm going to call this whole thing kernelization. Okay. This is not exactly kernelization, but almost kernelization. So let's stick to it. Okay. So what is the world? In this world, we just saw on this that okay. So suppose this is order 1, like say, like we are only seeing how many number of vertices can be reduced in polytime. Okay. In fact, notice I cannot even identify W of order log n size from where the solution comes. Even those things are not possible. Not only the whole side, even the relaxed nodes, and there I say, hey, W is something small sitting inside. Even that kind of transformation is not possible, because that also implies that you have to only enumerate from that subset. So it is not possible. Okay. And now we were able to come up with 2 power k square. Okay. So now I want to come up with a polytime transformation that reduces the number of, so this is somewhere here, like here is like no go. Okay. Somewhere here, not possible unless P equal to NP, right? Okay. So unless P equal to NP only implies somewhere here that like log K is not possible or this kind. And 2K square is possible. So now let's try to see what else can be proved from the right side. Okay. You understand my point? So can we reduce the number of vertices to say 10K, or say, can we reduce this to some order K or some such thing, right? Is it possible? And what kind of tools and techniques do we need to apply to reduce the number of vertices, or to come up with a polynomial time transformation for vertex cover such that in the reduced instance, number of vertices is upper bounded by order K? Is it possible, and how can we achieve that? Okay. So first, let's try to do some modest thing. Okay. So the modest thing is, okay, so is the overall goal clear what I want to do now? Right? So I told you, I just wanted to tell you that, look, 2K square is good, constant, not possible. That's all. So let's push, how much can we push from this side? Like how close can we push the number of vertices in this kind of transformation? Okay. So last time someone asked me, can we reduce degree to vertices? I would say, let's try. Okay. Let's try. Okay. So let's see. Suppose I have a degree 2 vertices, X, Y, and Z. Okay. Okay. X is the degree 2 vertices, Y and Z are some other vertices. Now, just to make your life easier, let's see. Suppose there is an edge YZ. Okay. So what is the first point? Degree of X is 2. Okay. N of X is Y comma Z. And second, YZ is in edge. In this case, can you come up with a transformation, or can you come up with a reduction rule? Imagine that you still have 0 rule, 1 rule, high rule, everything is there. But I want to also make the graph minimum degree 3 by getting rid of degree 2 vertices. And suppose this situation arises. How will you take care of this?
So to cover these 3 edges, this triangle,
Yes.
X, Y, Z,
Okay.
we need to have picked 2 vertices at least.
Correct.
So instead of picking X, pick YZ. So anyway, X will only cover YZ, but if the degree of Y and Z is like higher, then picking YZ is like on safe side.
Okay. So his rule is, okay, is G minus YZ K minus 2. right? So basically what he's saying, okay. So what he's saying, reduce g comma k to g minus y comma j k minus. Now we need to prove. Okay. So what is our claim that we need, or the lemma? Okay. G comma k is a yes instance if and only if g minus y comma j k minus 2 is a yes instance. Okay. So let me prove the reverse direction, which is easier. Okay. Okay. If g minus yz has a vertex cover S of size k minus 2, then S union y comma z is a vertex covered of size at most k for G. Does anybody has any doubt? Look, I deleted 2 vertices, and in the remaining graph, k minus 2 vertex could cover everything. I go back and put back this yj and say, hey, now every edge is covered, because the only edge which g minus yj doesn't contain are adjacent to either y or to z. And when I pick both y and z in S, every edge is covered. Okay, so this should be fine to everybody. Is this fine to everybody? If yes, put +1. Okay. Is there anyone who did not understand? Maybe people are shy. Okay, fine. So now let's show the forward direction. And this is what Sonak said, right? Is that suppose S is a vertex cover of G, then S intersection X, Y, Z is at least 2. Is this fine? Because look at a triangle, right? What are we getting? Here it is, X, Y, Z. Any vertex cover must contain, let's see, I think something funky happened. Let's wait. X, X, Y, and Z. See? See? It straightened up itself. Funky. This, apps are nice. Okay. So now for these 3 edges, can you cover all these 3 edges? If you pick just Z, then XY edge will be uncovered. If you pick X, YZ edge will be uncovered. If you just pick Y, these 2 edges will be uncovered. So definitely S intersection XYZ is at least 2. Okay. Now suppose X and Y is there in the solution, right? Then what is the role of X? Because look, then role of X is like a degree 1 vertex, right? Because it will be only covering XZ. Think that if YZ in the solution, you delete Y first. right? Then what is the degree of X? It becomes a degree 1 vertex. Then you already had a rule, pick Z, right? So whatever X can do, Z can also do in this case. So in either way, what is your this thing is that you look at X, you delete X, okay? You delete X, okay? And you add YZ. That's it. Now, because it has to have its size will not increase by like its size is not going to increase by adding YZ, right? Because think for a minute, either, or rather, let's say, just to make life more easier for this, let's say S minus XYZ, I deleted everything and I added back YZ. Definitely the size of S will not increase. Right? Why? Because out of XYZ, at least you know that out of XYZ, at least 2 people are there. Right? So when I do S minus XYZ, I have at least deleted 2 elements. Because S intersection XYZ is at least 2. Maybe all 3 were there for all that I care. I don't know. Right? But you deleted at least 2. And you have added back 2. Right? So size of S prime is at most K again. And what is the property of S prime? S prime contains YZ, which implies S prime minus YZ covers all edges in G minus Y comma Z. Done. Okay. So this is done. So if I had a degree 2 vertices which look like this, then you are done. Okay. But let's say, let's look at this situation. I'm quite sure you will not find this in book. Because it's not very, I mean, as a reduction rule, like nobody uses it because there are much more powerful reduction rules. But like at least for illustration purposes, this is nice. But I could also have a degree 2 vertex of this nature, no? YZ has no edge. What rule?
Remove X and add the edge by Z.
What?
Remove X and add the edge by Z.
So what will happen? And then?
G comma K is a yes instance, and then only G prime comma K is a yes instance.
Okay, so proposal. Sally, right?
Yes.
Okay, so here's a proposal from Sally, is that let's do the following transformation. Okay, so what she says that am I right, Sally? Let's call this graph.
Yes.
Right? So basically you are saying from GK obtain G prime by deleting X and adding the edge YZ. Am I right?
Yes.
Okay. And what happens to K? K remains the
Same.
Okay. How many of you believe that this is the correct? So now, if we believe her, we have to show the equivalence, right? Okay. So what? Then we need to prove the correctness lemma. Look, up until now, I haven't proved any correctness lemma because it was not required. It was very easy. But now, here, G comma K, yes, if and only if G prime K is yes. How many of you believe her? Okay. What a fan support. Friends. Just let's try to prove it, no?
So do we have any information about the degree of y and z?
Nothing. Did I write anything? That's all. All I know that degree of x is 2 and its neighbors are y and z.
So we do all the degree of yz is can be 1 also.
You can assume, I mean, I'm not assuming anything, but you can assume that that's not, because otherwise you would have applied a degree 1 reduction rule earlier itself. So you can believe that there is no degree 0 vertex, there is no degree 1 vertex, graph has minimum degree at least 2, for example.
So at least degree 2 yz.
Yeah.
Okay.
Okay. So like what I'm not able to understand, that imagine for the forward direction of the proof. Okay. Forward direction of the proof. Okay. That S contains X. Okay. S contains X. Then what happens?
Then it means all the edges incident on y and all the edges, sorry, all the neighbors of y are in vertex cover and all the z neighbors of z are in vertex cover. If you're saying that x is there in vertex cover, but y and z are not.
I'm
there.
not saying that. All I said
Okay.
S contains X.
Okay, okay. So I'm saying that if x is in vertex cover in G, then I can replace it with y or z. So if both of them are not there, then
So if x is there in the vertex cover, then both y z cannot be there.
Why?
So if say both y and z is there, then remove x.
Why? Okay.
It will decrease the size.
Fine. So suppose S contains X, then what you're saying, if S contains X, then both Y and Z may not be there. Okay, this I can agree. Because if both Y and Z are there, you can get a smaller vertex cover of size K by deleting X. Okay.
Then which one is not there, we can choose that and replace x.
What?
So both of y and z are not in the vertex cover. Suppose y is not in the vertex cover. So then we can replace x by y and it will still be a vertex cover.
I'm not understanding what you are saying.
Take the opposite case, like S doesn't contain x.
Okay. Then it contains YZ.
Yeah.
Yeah, so like we have to prove. I am not saying anything. Okay. So, okay. So S contains X, then let's say, okay. 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 So there are two cases. I mean, not that I was, okay. S contains X. Okay. Suppose S contains X. Then the first case is none of Y and Z are present. That's one case. And second case is one of Y and Z are present. Okay. And third, both y and z are present. Okay, let's see. Okay, now if both y and z are present, notice both y and z are present, then notice that s minus x is a vertex covered of g minus x, right? S minus x is a vertex cover of g minus x of size k minus 1. And since y and z are present, they are also vertex cover of g minus x plus yz, right? Of size k minus 1. So forward direction, at least in this case, is fine. Is that fine? Look, we are in the case that S contains X and both Y and Z are present. Then all I'm telling you that, in fact, then the G prime which you constructed by deleting X and adding the edge YZ had a vertex cover of size K minus 1. Because both Y and, look, you first delete X. It means G minus X had a vertex cover, S minus X is a vertex cover of G minus X of size K minus 1, right? And what did you do after that? You added an edge between YZ, but since Y and Z are already present in S minus X, they have a vertex cover of size K minus 1. Is that fine? Now, same argument holds even if Y and Z are present, because you delete X, S minus X is a vertex cover of G minus X, right? And because you present, you at least one of them Y and Z are present, you know that the edge YZ will be covered, right? So even in this case, I can produce, we can show that S minus X is a vertex covered of size K minus 1 for G minus X plus YZ. Okay. Now, none of Y and Z are present. So let's look at this. None of Y and Z are present.
Hello, sir. Can you hear me?
Yes.
Sir,
Yes,
can
sir.
you repeat again the second thing? I think like if say Z is already in the vertex cover. Okay.
Only
so,
one of them is there.
Yeah. Say Z is already in the vertex cover.
So first look at this. S minus X is a vertex cover of size K minus 1 for G minus X. Is that fine?
Yes.
Okay. Now, what did you add in G minus X? You added the edge YZ. That is what your G prime is, right?
Yes.
So if either Y and Z are present, that edge YZ is also covered, right?
Yes, but in original graph, who will cover that XY?
I'm only talking about the forward direction, no?
Oh, okay.
I don't know who covers it. In the forward direction, this YZ edge was not there, right? By our construction, there is no edge YZ. Okay. Okay. So let's see what her first case is. None of Y and Z are present. Okay. So now we know that X is here. Okay. None of Y and Z are present, which implies that for the forward direction, still S minus X is a vertex cover, right? S minus X is a vertex cover of G minus X. So this is perfectly fine, right? Of size K minus 1. I don't care about it. Now, what's it added? Added edge YZ, right? And to cover YZ, what she can do, she can take S minus X plus Y or S minus X plus Z and obtain a K-sized vertex covered of G minus X plus edge YZ. Is that fine? Because she has a budget of K, right? She never reduced the budget. So in this case, she covers every edge but YZ with the budget of K minus 1, because all those edges can be covered with budget of k minus 1. And for the edge yz, see either picks y or z, one of them, and that's your solution of size k. So forward direction holds. Okay. We'll see where we are dead. Okay. Why this is not correct, we'll see now. Forward direction is perfectly valid. Okay, I'll show you. Okay. Look at G prime comma K, and suppose S is a vertex cover of G prime and S does not contain YZ. What can I say?
In our construction, there is an edge YZ, no?
Yeah, you are right. So S does not contain, say, both YZ. Okay, fine. Doesn't contain both Y and Z. Fine. You're perfectly fine. Suppose my solution is, yeah, it contains this, it contains all the neighbors and some other vertex. Now, there is X here in the original G, which has an edge to both Z and both this. Now, red can be taken care of, like this X and the red edge can be covered, but for XZ edge, who will handle? I need to add either X or Z.
Then S is not a vertex cover in the first place, right?
What?
Because of the edge YZ, we need to cover the edge YZ.
Yeah, that's why you're covering this red edge, no? That is why you're covering with this red vertex YZ edge, no? You are covering the edge YZ with the red vertex. It's just that you are not picking both the endpoints of that edge.
Okay.
I am just saying, and S does not contain both Y and Z. Okay? Say, rather, Y is in S and Z is not in S. Okay? Now, how will you construct a K-size vertex cover starting from this S for original G?
So X is there in the vertex cover.
What? We are talking about the reverse direction. S contains, okay. We did not complete even the forward direction. We said forward direction, if S contain X, we can do. Now I say, okay, let's try to see backward direction. Maybe if S doesn't contain X, we can do something. But suppose in the reverse direction, I see some problem already. Okay, in this reduction rule. Okay, so what's the problem? Suppose I try to prove reverse direction. Okay, and I start with a vertex cover of G prime. Okay, it's a reverse direction, right? Suppose S is a vertex cover of G prime and S does not contain both Y and Z. Can I look? We are discussing, we are not proving this. I don't know whether this reduction rule is correct. I just took one case in the forward direction and I was able to complete the proof. Similarly, I took one case in the backward direction and I'm trying to see if we can prove it. And I see there's an issue here. I do not know if you give me a vertex cover of G prime and S that contains Y and doesn't contain Z, I have absolutely no idea how to make S, starting from S, a vertex cover of size K for G. I absolutely don't know because S itself has size K. Does people understand what my issues are?
Yes,
Yes.
Okay. Look, I don't think this transformation is legitimate, okay, personally. But I just wanted you to go through the grill to understand when you try to prove how you encounter difficulties and you have to do some modifications. I'm failing on purpose, but I just wanted to say that where will you fail, right? Some situation we can handle, like for example, in the forward direction, if S contains X, and if S does not contain X, that's obvious because then you contain YZ, both, right? Then the forward direction will anyway hold. What is to prove? In the forward direction, if S does not contain X, then what does it will contain? Both YZ of size, and then okay, you added one extra edge, then what? Y and Z is there, so that is covers that edge, right? In the forward direction, so forward direction will hold irrespective of whichever case you are. S contains X, S does not contain X. You're still good. Okay, fine. But the reverse direction does not. So in this transform, so what did we learned? Learned that.
So in this reduction, we are somehow missing the fact that this YZ is not connected in the original block.
Of course.
So we are somehow to incorporate the fact that this YZ are not at this.
So we have to incorporate the fact either X is there in the solution or X is not there in the solution. If X is not there in the solution, then both Y and Z are in the solution. So we will do the following transformation. Learned that above transformation does not work. Okay. Okay. So let me tell you what works. It's almost there. So here it is X and here it is YZ. Okay. What I do, I make a big fat vertex called YZ. Okay. Okay. So first I do what? I do G minus X. Okay. I make a new vertex YZ. Okay. So G minus X, I make a new vertex YZ and add WYZ and edge if W belongs to neighborhood of Y or W belongs to neighborhood of Z. So picturesquely what happens is that this is how it is, right? Maybe it is like this. Let me draw one concrete example so that you understand what's happening. Suppose I have X, Y, and Z. Suppose they have a private neighbor W1, W2, W3, and they have some common neighbor, say W4, W5, and suppose they have some private neighbor W6, W7, W8. Now what you do is that you first delete X, and now you make YZ, okay? And YZ is adjacent to W1, W2, W3, W8. That's it. This is what my transformation is. Okay. But, so suppose this is how I get G prime. So what is my rule? Transform.
So we are doing contraction.
What?
Contraction. Oh, no, it is not.
I mean, there is no edge between Y and Z, but that's sort of contraction, or I would call it identification. Okay, let's call it. I mean, I don't want to give it a name. Like, if you really want, identify Y and Z. Okay, contraction. I want to use it. I mean, like, there's a proper meaning for that. So identify Y and Z. Okay. So we transform this. So for a minute, let's just look at this. What happened? I deleted X. So basically, I rather say I deleted X, Y, Z. Okay. Made a node YZ and added some edges, right? So you delete all X, Y, and Z, Now you added a new vertex called yz, and you made yz adjacent to every vertex which was adjacent to either y or adjacent to z. Is the transformation clear to everybody? If yes, please put +1 in the chat. Okay, good. So now let's prove correctness. Okay, let's see if we manage to do this. Okay, let's prove the forward direction. Okay. X is there, yz is there. Okay. Notice so suppose S is a vertex covered, S is a vertex covered of G. X belongs to S, right? If X belongs to S, then what do you know? Then what do you know? Okay. Okay. Either
both do not belong to.
Right? So let's look at the case when X belongs to X and say X belongs to S and Y comma Z does not. Okay, let's say. I don't know what is easy. Y belongs to S, Z does not belong to S. Suppose this is the case. How will we handle this? This is easy, no? Right? You do X minus XY plus XY. No, plus YZ. Sorry. We have a vertex YZ, right? Here. Big. So I deleted both X and Y, added a vertex YZ. So whatever Y could cover, whatever Z could cover, YZ could cover. Is that fine? Excellent. Right? So what is its size? K minus 1. Right? Now, X is there and one of them, but it could also be that X belongs to S, Y does not belong to S, and Z does not belong to S. Right? Then claim S minus X is a vertex covered of G minus X and hence G prime. Look, because you are not picking Y and Z, it means you have picked up all the other neighbors of Y and Z into your S. Right? Look, since Y does not belong to S, Z does not belong to S, implies N of Y is a subset of S, N of Z is a subset of S. So if you don't pick YZ, you are picking all the neighbors anyway. So you can show that S minus X is the vertex cover of G minus X and hence also G prime. Of size, how much? K minus 1. Okay, so this is why we clubbed these two vertices. Okay, now look at the case when X does not belong to S. Then what happens? Y belongs to S and Z belongs to S. Right? Then what are they going to do? S minus YZ plus single vertex YZ. That is a vertex cover of size K minus 1. You deleted 2 guys, added 1 guy. So we were smart here. Right? If we knew that these two vertices are going, what edges they could cover? So I found a vertex which does exactly the same job which both Y and Z together could do. Right? So I found a vertex YZ whose neighbors were precisely the neighbors of y and z. So this is where we are using the fact that we have identified the neighborhood of y and neighborhood of z. Okay. Now, reverse direction is again obvious. Okay. What is that? S either contains what? Yz, that's the first case. Then in case, what will you do if S contains Yz? Okay. You do S minus Yz and add Y comma Z. So whatever Yz could cover, Y and Z together can cover, in particular, as well as they can cover the edges which are adjacent to X. So this is a vertex cover of size K. You deleted one, so you got K minus 2. You added 2 Y and Z, so that's there. Okay. S does not contain YZ. It means S contains all neighbors of YZ, and in particular, all neighbors in G but X, right? Look at this. Y and Z, right? If you're not going to contain him, then you have to contain all its neighbors, right? So if you go back in G, what happens? You basically, Y and Z, these edges are still covered. What you are not able to cover? X, which is, and the edges corresponding to this. But for that, you do have a budget of how much? 1, right? So what you will do, you will say, I add S plus X in this case, right? And then we have a vertex cover of size at most K for G. Okay, so you can argue, if you do this transformation, you can argue that, you know, and look, it's a very interesting, because you are dropping K by 1 in this case, right? This is a transformation which actually very non-trivial transformation, because actually it reduces the K by 1. So if you have lots of degree 2 vertices, I mean, every time you apply this transformation, right, you're going to lose something interesting. But you have to also notice that this vertex makes a vertex of very high degree, potentially very high degree, because maybe I'm a degree 2 vertex, but Y had degree 5, Z had degree 5. So when you merge them, you might get a very high degree vertex, right? So this is a very non-trivial transformation for vertex cover. But at the end of this, what did we achieve? We achieved that the minimum degree is 3. By the way, this will not give us amazing something, but it is one of the useful heuristics for vertex cover in practice. Okay, so what did we achieve now? Delta of G is at least 3. Okay, and what is the maximum degree? Is at most K, right? So what is summation of degree V? At most, okay, if you recall correctly, summation of degree V is at most 2m, which is at most 4k square, because m was at most 2k square. Every vertex has degree at least 3, so 3n. So what is n? Hey, we made some progress. 4 by 3k square, better than 2k square. No? Number of edges was 2k square, or was, no, it's wrong, no? M was at most k square, right?
Edges were,
Yeah, this should be 2 by 3. Look, how many edges we had in the graph? K square. K vertex can only cover k square edges, right? Because maximum degree is at most k. So every vertex can cover k edges. So k vertex together can cover at most k square edges. So 2 into m is 2k square. Is that fine, Nidhi?
Yes.
Okay. And the summation degree v, every vertex has at least degree 3. So summation of degree v is at least 3n. So n is at most 2/3 by k square. Hey, great. So let's look at our achievement bar. Okay. We made some progress, no? We went here. 2 by 3k square. Okay. Is the reduction rule for degree 2 clear? We may never use this, but like, I just wanted you to have some fun transformation to see.
Sakib, I have a question.
Please ask, Nidhi.
So in the reduction rule, y and z has a neighbor x. Can they
Yes.
have any other common neighbor if y and z doesn't have an edge between them? So the second case where we consider that y and z
What are you
doesn't
saying?
have an, okay.
Look at this. Yes, like this.
Yeah.
Okay.
So now the case we consider in which, yeah, so can they have a common neighbor?
Yes, why not? They can have. Look at my transformation. No, I did keep some of them, right? If you look at W4, W5, right? They are common neighbors, right? Y, W4, Z, Y, W5, WZ, Z, right? They are common neighbors, right? But here, yeah. Now with respect to Y and Z, it will become parallel edges, so I deleted it. So it's just a normal.
Okay.
Where in the proof we use that it has no other common neighbor. That's all that you have to worry, no?
Yes.
It isn't like, we don't look, these transformation, we shouldn't be looking too much into the graph. How much ever local we can see and make some rules is what we try to do. We will make some global rules, but like here, all we try to make is a local rule. Okay. Now, I want to have some slightly more non-trivial transformations, okay? I want to go slightly much below, okay? Now I want to ask you, what could be situation similar to degree 1 where we could apply rule similar to degree 1. So what was the degree 1 rule? We say that, look here. So look at the idea of degree 1 rule. Okay. So we said, look at X and look at Z, right? We said, pick Z because Z can do as good as X, right? Or rather, whatever X can do, Z can do. Or if my S contains X, then S minus X plus Z is also a solution, right? I mean, this is what we were saying all the time, right? You know, what other situation we can say something of this nature? Okay. So let me draw one situation for you and then let's see if you can.
So if there is a vertex of degree D
Okay.
Say, and D is like greater than equal to 3 or and less than equal to K. And
Like,
all the neighbors of this degree D vertex forms a clique.
what do you mean? This, like this situation?
And
And
yeah, and this 3 neighbors forms a triangle.
okay.
Then we can also like same degree 1 type rule. We can,
Sure. Yeah, this is also fine. But I wanted to draw something very similar. Okay, slightly different. Okay. Uh, in this situation also we can apply degree 1 rule, no? In this situation, can we apply this rule? This is exactly how the graph looks like. Suppose. What rule can you say and why? This is exactly how it looks like.
we can include W1 and W2 and delete W1, W2 and reduce the size by 2.
Okay, let's see if others agree with you and why. Anybody else which would like to say, add something? So he has some point, and let's see if someone else can add why. He says the rule is following. If you see such situation, then what he says is G minus W1, W2, K minus 2. If you see such an object in a graph, situation like this, and a graph could be like this. Okay.
I think we can remove W1 and decrease the budget by 1. No,
that I'm not.
The same.
Huh? He's saying something different. He's saying let's delete both W and W2.
Then I think budget should decrease by 1 only because neighborhood of W1 is contained in neighborhood of W2. So even W2 is covering all the neighbors of W1 as well.
What are you saying? I don't think so. Think about it.
Neighborhood of W1 is contained in neighborhood of W2?
And even if they are, so it's not dominating set.
Yeah.
Say it's not dominating set.
Yeah, sorry.
Why? Someone has to tell me a reason.
Here A is a degree 1 vertex. So if we, so by degree 1 rule, we should pick W2 and reduce the size by 1. And if we pick W2 and delete W2,
let's imagine that there is no degree 2 vertex. If this is what, like, otherwise that's like, okay, my mistake. Okay, I'm sorry. Like, okay, if you want to really make life harder, because then you will say, let's apply degree 2 rule. Okay, imagine that. Okay, let me see. Making examples are not that easy. Like, okay, just that you cannot apply degree 1, degree 2 rule. I have to do something, no? Okay. W1, W2, W3, A, B, C, D, E, F, G, H. Okay. You can't apply degree 1 reduction rule. You can't apply degree 2 reduction rule. Now what? Like, it's a complete bipartite graph between A, B, C, W, F, W, and W2, W3. And of course, there's a graph hanging on them. Oh no. Okay. There's a graph hanging on them. Okay. Here, of course. Like this part is only this much, but like W1, W3 could be connected to the world. Just like a single, like just like a neighbor of a single degree vertex could be connected to the world. And this is how it looks like. Okay. Then I'm sure Sonak will say, okay, then in this case, you have to take W3 and
Sir,
degrees.
we are basically contracting a click inside the graph into a single vertex.
Click. Where's click?
I mean, this is K3, some 1, 2, 3 can be contracted into a single vertex with self loops. I mean, in contraction of W1, W2, W3 into a single vertex.
No. I'm saying that this reduction rule is correct. Can you justify this?
This is
So neighbor of W1, W2, W3 are higher in number. So taking
what number?
Higher in I mean, more than 3. Neighbors of W1, W2, W3 are more than 3. So instead of taking all those neighbors, taking W1, W2, W3 is good.
No, doesn't work. There is some region. I mean, there are some numbers also as supple.
This thing, this A, B, C, D, E, F, and W1, W2, W3. This is a bipartite.
Maybe
So,
W1, W2, W3.
there could be an edge between W1, W2, W3. I have never told you that. It is, if I look from the W1, W2, there could be an edges here. I don't know.
But we are taking W1, W2, W3 in the vertex. So those edges will be covered.
So why complete bipartite graph? What is bipartite graph has to do with this?
So this
like there has to be some more scientific reason. Yes, I mean, I'm not saying any of you are saying something wrong, but none of you are saying what you should say yet. But you all of you are in the correct path. So think. I have no hurry. It's 10:29 anyway, so I have 3-4 minutes. So it's not that I'm going to prove it formally anyway. So let me fight with your intuition.
Because there are no edges in the neighborhood of W1, W2, W3, and that's why we can remove this and decrease.
It's just that, like, okay, let's go back to degree 1. I don't think we all have understood degree 1. What did we say? Or rather, let's go back. We wrote, no? Pick Z because Z can do as good as X. Right? Right? So if S picks any vertex in ABCD, then you have to say, look, forget those ABCD. I can make my job from W1, W2, W3. You understand what I'm saying?
Is it because ABCD is an independent set? Like,
yeah, they are independent set, but that's one part of the story. That's perfectly correct. Okay. But we have to also say that, look, if my solution picks ABC, some vertex from ABCD, then I can do the job from W1, W2, W3. And first of all, like, okay, let's ask myself. I'm definitely deleting 3 vertices from here, W1, W2, W3. How are you even guaranteed? Think about, first of all, how can you guarantee that from this part of the world, A, B, C, D, E, F, W1, W2, W3, you will at least pick 3 vertices in the vertex curve? Is this even guaranteed? I mean, you understand my point? Like, we went deterministically deleted W1, W2, W3, right? Who guarantees you? Okay, so there's some min max playing a role. Okay, look at this. What is this? W1 and B, W2 and C, and W3 and D. What is this? They look like something.
Matching.
They are matching. Yeah, they are matching, which implies what? every vertex cover must pick at least one vertex from here, one vertex from B or W1, other vertex from C or W2, or other vertex from D or W3. Is it true? Every vertex cover either selects B or W1 and C or W1 and D or W3, right? You are forced to pick at least every vertex cover of size at most k. In fact, any vertex cover must pick at least 3 vertex from here. So now if any vertex picked up C and say picked up B and picked up W3, suppose it picked up, and maybe it also picked up E, for all that you care. What happens if I say forget C, pick up only W1, W2, 3, you still have picked up only 3, and you have done everything any minimum vertex cover ever can do in this part of the world. You have to prove this. I'm not saying that we are done, but this is exactly what it is. That every minimum vertex cover from this part must pick 3 vertices, okay? Must pick at least 3 vertices, and W1, W3, W2, W3 can do anything as good as any 3 vertex you can pick from this side, similar to degree 1 vertex. Think for a minute. I'm not going anywhere. Why Koenig's theorem and this and that? Like, don't throw things, man. Look, I have drawn for you. There's no Koenig theorem. I have drawn matching for you. And like, yeah, Koenig theorem only tells us that every minimum vertex cover is equal to maximum matching in bipartite graph. But this is not bipartite graph. It's some portion of the graph. Okay, because there are edges between W1, W2, W3. So maybe you're forced to pick something from here. But like, all I'm trying to tell you that because of this matching situation here, you are supposed to pick at least 3 vertices from A, B, C, D, E, F, W1, W2, W3, because we have a matching BW1, CW2, and DW3. Now you look at any vertex cover here, any vertex cover. Okay, any vertex cover can happen what? Say it could pick some vertex from here, some vertex from here, some vertex from here. I don't know, any vertex cover, right? Now, what will I say? Look at S minus A, B, C, D, E, F, W1, W2, W3. Okay? Plus W1, W2, W3. Now, because we have a matching of size 3 hidden here, we know that when you delete this whole A, B, C, D, E, F, W1, W2, W3, you are at least deleting 3 vertices. Because among them, you have a matching of size 3. Now, what are you doing? You decided to add some 3 back, and you're claiming this is a new vertex cover. S minus this plus this is a vertex cover. Right? And the size can only drop. It can never increase. Is this idea clear to everybody? Or everybody is confused? Satya, is it okay, or are you confused? Satya, is it okay, or is it confused?
Yeah, fine.
Sonak, I'm going to ask one by one individually.
Yes, it is clear.
Madhumita, Sovik,
Yeah,
Ananya, Ankit, Pallavi, Sayani, Hemika.
it is clear.
Okay, fine. So it is not about Koenig. Those things will come when we have to find such a structure. We'll get there. But here, it is just that locally, I'm able to find a vertex cover which is equal to maximum matching. So it's like in local min-max theorem, if I can apply, I can take this concept of local min equal to max and use that local min-max to apply reduction rules. Okay, so it's like it just happened. Okay, right? So we able to find a situation where we are correctly identify some subset of vertices, and we are saying, look at any minimum vertex, look at any vertex cover minimum or non-minimum from this position. Then whatever that vertex cover can do, this 3 vertices can do as good as this. So let's delete anything from S, which is from this portion. And because of the matching, you are guaranteed that you have at least deleted 3, right? And say, now let's put back the canonical vertex cover from here. And that's it. So it is exactly like degree 1 rule. So we said, look at S and delete U or V from this edge. So you have definitely deleted 1 vertex and you have canonically added 1 vertex. That's it. Right? So here I have deleted A, B, C, D, E, F, W1, W2, W3. This I am guaranteed because B and W1 is a matching. So at least B and W1 is there. So I have at least deleted 1 vertex from here. C or W2, at least one of them did. Maybe both are there. So I have at least deleted 1 vertex. Oh, D and W3 is also, one of them is there. So I have at least deleted 1 vertex. So when I delete S minus A, B, C, D, E, F, W1, W2, W3, I have definitely deleted 3 vertices. And how many vertices am I adding? 3 more vertices I'm adding. Now, with respect to the covering property, look, any vertex in BCD can only cover edges which is going to W1, W2, W3. So by picking W1, W2, W3, you are picking anything that A, B, C, D, E, F can cover, right? And these can cover more because they have much more neighbors. But A, B, C, D, F, they did not have any other neighbor but W1, W2, W3. Right? So this is exactly what happened. So in some sense, W1, W2, W3 is as good as anything your vertex cover could pick from here. Okay? Okay. So the good way of learning in my class is to just be in the moment. I try not to use theorem statements as much as I can. I will get you to those theorem statements like fluently on a way. Like, don't worry about those. Okay? Like, you don't have to know the theorem statements. Okay? We will get there like naturally. So what we need here, like, okay, so what property we had? If we try to understand those things, we will get to Koenig's theorem, Hall's theorem, all those kind of things. But like, okay, this is also one reason of not teaching that in a graph theory course, because I will have an opportunity to teach somewhere else anyway. Okay, okay, all good. If that is fine, then we will meet on Thursday at 9:30. Have fun tomorrow. Okay, I will also get to do something else tomorrow. Okay, so good night. Unless you have more questions, I'm done for the day. Look, my whole purpose is to teach most of the things of this course in the class. I'm not zooming at the speed which is very fast and trying to be with you, trying to address your intuition in the class itself. So it would help you if you are more vocal, ask questions. Okay, all done? Then good night.